and stay on topic. I think on Thursday I kind of jumped the gun a little bit when I wrote that chart. I was kind of making one of those charts today. Okay, so I also jumped the gun talking about electronegativities, things like that. So we might have a really small lesson today, because I'm pretty sure, right, on Thursday I talked about electronegativity difference. Okay? As we go to the left, as I go left to right, it becomes more electronegative. As we go top to bottom, it becomes less electronegative. So the trend is really from the bottom left to the top right. That's really the trend. As I go from the bottom left to the top right, it becomes higher electronegativity values. As I go from the top left down to the bottom, top right down to the bottom left, I have less electronegativity values. Okay? Now, when we're talking about bond type, what is really the number one thing that tells us what type of bond is going on?
Metals / non-metals.
Okay, that is the quick way of identifying, but what is the reason behind why something bonds ionically? Difference in electronegativity. Okay, we quickly identify by looking at the periodic table and look metal, non-metal, but the best way to identify is their electronegativity difference. It just so happens that we can do it a little bit quicker with little thinking, just by saying, oh, metal with a non-metal is ionic. But the reason why metal and non-metal is ionic is because a metal has a very, what electronegativity value? Low. And non-metals tend to have high electronegativity values. So that's why we can just say a metal or a non-metal bond ionically. Okay? It's a quick way of identifying it, but if you guys don't know the why, you're going to struggle. Are you even in the room?
Yes. I actually did something.
Well, pull out your notes, start scribbling down what I say. Be doing something to listen.
Alright,
Did you know
I listen better.
Okay, do you know if you're doing more than one thing, you have less focus on any one thing while you're doing that multiple things?
Something that would make that actually impossible to truly multitask. We're switching back and forth really fast.
That's what science says.
Yeah. That's why you can't listen to music and do homework well at the same time.
Well,
As
that's
well.
classical.
Well, yeah, you can't listen to words.
Yeah.
Or like, listen to something in French if you don't understand French, not in English. I don't know how to do French. It's too Latin for me because it's like classical choir songs, but yeah.
It's like
Sorry,
texting
that's
around.
wrong.
I realized you didn't write it off the road. Okay? So the relationship between electronegativity values and bond type is shown on table 8.1. I don't find what page that is. Chapter 8 of your books. I don't see you. There you go. 346 is what I'm looking for. And we kind of did this in we did a much bigger table the other day, but you can see this here. The way to really determine bond type is with the electronegativity values. So if you look, we have, in your book it says covalent. It really should say non-polar covalent to be more precise. They're just saying anytime you just say covalent, you're referring to non-polar. Okay, so that's what they're saying when they just say covalent. So be very careful. If they're trying to talk about polar covalent, they will have to say that. Okay? But if you look here, you can see that your non-polar covalent have no difference in electronegativity. Your polar covalent, you're starting to have a difference in electronegativity values, so therefore are the electrons being shared equally? Are the electrons being shared equally? If they have differences in electronegativity values, they're not being shared equally. The bigger the difference, the more unequally they are being shared. Now there is a breaking point that we say they actually don't share anymore. What is that breaking point? When you start getting into what type of bonding? Ionic. Okay, now, we've talked about this, but is this actually true? No. Okay? There's no metal up here that has no desire for the electrons. It's just so polar that we give it a new name. Okay? Now, what I want you to do is order these bonds in order of increased polarity. Now, what causes polarity?
Difference of electronegativity.
Object about to start.
That's what the definition of polarity is. What causes it is electronegativity. The greater the difference in electronegativity, the greater the polar charge is, or polarity. Okay? So what you need to do, if you don't know these electronegativity values off the top of your head, you can look in your book. However, I think these are close enough that you can kind of use just the trend to figure it out. Now, yeah, I think the only ones you might have trouble with are this one and this one. Okay, but if you remember the intermolecular force topic that we talked about last year when we talked about the hydrogen bonding, and hydrogen when it bonds with nitrogen, oxygen, and fluorine, it creates a really strong intermolecular force. That should help you answer that one. Okay, give it a try. Try not to look at your book. Still working? Yeah, this warm weather is going to put my students to sleep. Not warm weather, warm room. You guys just look hazy. I feel hazy. Long weekend? Why?
Thursday night, my sister's dress rehearsal, dinner, Friday.
Oh, wedding, yeah. Forgot to skip my workathon group for that. Okay. That was far more valuable. Okay? Alright, so what is the very, very obvious one as I go from... I didn't even ask the question. Nice. Thanks. So HH. And if we were to actually look up their electronegativity values, I think it's 1.1. Let me see here, yeah. So 1.1 and 1.1 gives you a change in electronegativity, 0. 1.1 or 2.1? 2.1, sorry. I said 1.1 but wrote 2.1, is that correct? Oops. Do it as I say, not as, no, do as I write, not as I say.
What? Never heard that.
It was the same as
I know, I did. Okay, so increasing polarity, so that has the least. What's next?
Probably SH.
Okay, anyone disagree with that?
It'd be FH. No, it's not.
No, I mean, that's
What
what
is
I
that?
think.
I think it's the biggest.
Oops, I did this one.
Okay, we know that hydrogen is a 2.1, sulfur is actually 2. Holy cow, now I'm writing and I'm just, is it hot in here? It seems hot in here.
Your fan on?
Wait, how are we supposed to know this?
No, you're not supposed to know the actual numbers, but I'm just showing you the actual numbers. You can look at the trend and figure this out just fine. Did you not even do it?
No.
You see
I
it?
don't know how to do it.
That's supposed to go up.
Are you kidding me?
That's right.
Lowest electronegativity, highest
No, but
electronegativity.
hydrogen is random over there.
It's not. You don't remember that hydrogen's right in the middle?
No.
But regardless, they're all with hydrogen. So really you're just looking at which one's the most electronegative. This is a constant. So you're just looking at really the one that's not hydrogen. Okay, getting a little bit more difficult. What's next?
It's chlorine, right?
Yeah. So this is, I think, 2.8. Is that right? Nope. 3.0. Again, you're not going to have to show the difference in electronegativity or remember each particular element's electronegativity value. But it's good to see this so we get a good idea of which one, because it isn't a perfect trend, and I will show you why here in a sec. What's next?
O and H.
It was toss up for me between chlorine and oxygen.
Oxygen is actually significantly more electronegative.
Okay. Is that one of the instances where the row is then is more chlorine than the?
Well, it kind of depends. Do you remember hydrogen bonding at all?
A little bit.
So it's the strongest type of intermolecular force, and it's when hydrogen bonds with three elements. Do you remember which three elements?
Oh.
Oxygen,
Nitrogen,
nitrogen, oxygen, and
Carbon.
fluorine, and fluorine. NOF. You remember the NOF? NOF?
No, actually.
Okay. These are the three most electronegative elements on the periodic table.
Alright.
Now, nitrogen and chlorine actually are identical. They're both 3.0. Okay, so you could probably throw chlorine in there and still call it one of the hydro. But they, for whatever reason, they said that hydrogen bonding is specifically those three, and it's because they're the most electronegative.
Oh, yeah, I remember that now. Okay, yeah.
Okay, and lastly, fluorine. All right, so if I were to talk about this based on bond type, I would say as I go this direction, I'm becoming more covalent or increasing in covalent character. And as I'm going this way, I'm becoming more ionic, even though we know none of these are ionic. But remember, covalent and ionic are just words that we use to describe no polarity, high polarity.
From right to left, it decreased 0.5, except for the last one.
Nice assessment.
This is where they round to. Is that why it's that way?
I'm not sure. I have no idea why, if it's actually specifically those numbers, or because those are some random ones that were chosen. If you did like sulfur or something, no, we did sulfur. We did like bromine, it's like 2.8, and iodine.
Yeah.
So,
This doesn't have to be that way.
no, it's just, yeah, this group. Okay? Questions so far? Am I spending too much time on this? You guys are all good with this? All right, dipole moment. We'll be doing Lewis structures showing our dipole moments. And I'm trying to remember this 2 o'clock schedule. I don't ever have it anymore. 22. How do you know that?
Maybe everyone
But I had every Wednesday last year. I could remember it.
I couldn't remember.
I mean, I guess I'm not getting up and leaving at the same time every day. I'm not looking forward to that time so I can leave, like all my students are. Just cannot wait to be done with Mr. Kramer's class. I just want to run right into a wall. All right, dipole moment. Okay, it's a property of a molecule whose charge distribution can be represented by a center of positive charge and a center of negative charge. Okay, so if you remember, we did Lewis structures of these guys, and we showed polarity. First of all, did I define polarity last section, or we not even define polarity? I mean, I've defined it in years past, but I don't think we ever defined it. Okay, it is opposite regions of opposite charge, and it's created by what? I've already said it, but what is it? What creates polarity? Differences in electronegativity. Thank you, Annie. So if we look up here, we follow our trend, we realize that fluorine's more electronegative. What does that mean, or what is that going to tell you about these shared electrons? Yes, they're unequally shared. And they're pulled more by the fluorine because it has a higher electronegativity value. Okay? What this does is creates polarity. We have a positive end of the molecule and we have a negative end of the molecule. Where is the negative end going to be? The reason why the negative end is going to be near the fluorine is because you have a pull of electrons towards the fluorine. So our dipole moment looks like that. Okay, here's the positive end.
What's between us?
No, it's a Greek symbol for polarity. I don't actually know what the symbol is, what it's called. This is showing partial charge. Partial positive charge, partial negative charge. Now, here's how you can kind of think about this dipole moment. What does this look like? Just that spot right there. I heard you. It's a plus. Okay? That's going to be in the side of the molecule that has the partial positive charge. And the arrow is going to be pointing towards the more electronegative element, or the more electronegative, or which side of the molecule is getting the electrons pulled towards. Does that make sense? Okay? The arrow is showing where the electrons are being pulled. This little positive here at the end of the arrow is showing where the positive end of that particular molecule is going to be. That's how we show dipole moment. Okay? Because when you get electrons, remember, if these guys were just sitting side by side and they weren't bonding at all, wouldn't these both be neutral atoms? Right? I'd have one proton and one electron here, 9 protons and 9 electrons here, they'd be neutral. But as soon as you take the electron from the hydrogen and pull it this direction, isn't that going to make this proton exposed and give this a little bit more electrons than it has protons? Yeah. Are you seeing where the partial charge comes from? Okay? Now it's this charge, the positive and the negative charge, that is used to hold other neighboring HF molecules to itself. We'll talk about the intermolecular forces in a different chapter. But what ends up happening is a hydrogen from another molecule, HF molecule, will be directed towards the negative side of the fluorine here, and so forth. And those charges is what holds them in the liquid and the solid state. You guys remember that at all? What did you say, Mr. Kramer? I wasn't paying attention. Yeah, that's the last word I said. You are right. Good for you. All right, now it says some molecules have polar bonds, but do not have a dipole moment. Why?
Because like CH4, it balances out.
Okay, good. So I want you guys to turn in your books to page 347. There's another way of representing polarity, and it's called, or charge distribution, and it's called electrostatic potential graphs. I'm not going to make you do them. I mean, it would be kind of fun to pull out colored pencils and start drawing these things. Everybody on 347? Nope, not Emily.
Well, the one top corner is.
Okay? So if you look at the very side, we're going to read these, look at these from left to right. Okay? Looking at figure 8.5, you can see the Lewis structure of water. Do you see where it has its charge distributions? Hydrogen side of the molecule is what? Positively charged. Oxygen side of the molecule is negatively charged. And why is that? Okay, oxygen's more electronegative. And then the next little picture it shows you the dipole moment. Okay, and then in C you can see they make these little graphs that show really where the charge distribution is. The more blue a color is, the more positive the region, or the more electron deficient it is. The red regions are the more electron dense the region is. So red is where it's most negative, blue is where it's most positive. Okay? Right, now let's look at 8.6. You can see the same thing. Okay, it's not quite as polar. You don't see any really strongly blue sides, or something that, we don't see a really huge red side, but is there still polarity there? Do you still have opposite regions of opposite charge? Yes. Now that might tell you that NH3 might exist as a liquid, or as a really volatile liquid at room temperature. Versus water is a little bit stronger because it's got a bigger charge distribution. Now let's look at CO2. First of all, what does CO2 exist? What state does it exist at naturally at room temperature? Gas. And the reason why it exists as a gas is because it's non-polar and doesn't have opposite regions of opposite charge. Now, does that mean it doesn't have a charge?
No.
Look at it. A lot of charge. But the two opposite regions are both what?
Both negative.
They're both negative. So what you have is, if you look at that far left one, you got the positive regions right in the middle, and the negative regions are on the outside. So we still have polar bonds, but they pull in opposite directions. Therefore, if I have CO2 molecules here, and I put another CO2 molecule up to it, is there much attraction force here?
None. Push it away.
Okay? Now we can get CO2 to exist as a solid. Give me an example. What is solid
Dry
CO2?
ice.
Dry ice. Okay? Now, when we get into the intermolecular forces, we will talk about what allows these things to actually attract. Okay? Has to do with the condition, but also has to do with how dispersion forces work. Okay? So, just trying to get you to see that because we have a polar bond, does not necessarily mean we have a polar molecule. We do have opposite regions of charge, but they're not opposite charges. Right? Was the opposite ends of CO2, was there a charge? Was there a charge? Yes. But they were both negative, and so they weren't opposite charges. Okay? All right. Woo! Seems like I need to shorten this a little bit. Okay, so here's what I want you to do. I want you to draw all four of these Lewis structures and show dipole moments if they have them. You got them all done?
Yeah, I don't know how to do that, so
I haven't showed you Lewis structures, have I yet? So I'm kind of having you guys do Lewis structures based on what you remember from the past. You don't have any idea?
Wait, it's pretty evenly?
got this first one fairly easily. Yeah? Okay. Anybody think they got the sulfur or SO3? Think you got it? Yeah?
No, I got it wrong.
Okay. Now this one actually has resonance. I don't know if you guys remember that, because the double bond could be any one of these three locations. And actually, the bond is not actually two single bonds and one double, it's actually three hybrid bonds in between a single and a double bond, which is kind of goofy. Okay?
We need to throw them off your list.
You can, yeah. Yeah. But I'm not going to make you do it right now. All right, it's actually a four. Each of those bonds is a 4/3 bond, which I know kind of probably doesn't make a whole lot of sense at this point. But okay, now this is also going to be nonpolar, so no dipole moment. But notice, each bond is a polar bond. So if I were to show the dipole moment, I know you technically don't show dipole moments for the bonds. Dipole moment is specifically for the whole molecule. But if I were to show a dipole moment for the bonds, they would look like this. Which means this is going to be negative, that's going to be negative, that's going to be negative. And where's the positive region of this guy? Right in the middle. Okay, still nonpolar. Okay? Same thing with this guy. Does this have a dipole moment? Does that have a dipole moment? No, does not have a dipole moment. But does it have polar bonds? Does it have polar bonds?
Yeah.
Yeah. Okay, it just so happens that they pull equal and opposite in both directions, that what ends up happening is, I'm trying to think which one's the more, I think carbon's more electronegative. Yeah. So what you end up having is a really dense region of negative charge right in the middle, and the outside's all positive. Well, what is methane at room temperature? CH4 is gas at room temperature. Should make sense, right? There's not much attractive forces holding these guys together. Okay, last one. I told us it was a bent structure. So this one does have a dipole moment, looks like that. You can put it through the molecule if you want. I choose to usually put it beside it, even though it probably doesn't give a super great accurate arrow as the direction of pull. Okay, any questions?
Can you do the Lewis structure for SO3? Like, show.
Slowly.
Yeah.
Good question. Nice, I like it. Make sense so far?
Yeah.
Single, single, single. Now I can choose, if you look at this, I got 2, 4, 6, did I do that right, did I? Did I do that right? Yeah, I did. Okay? So this is going to be trickier. Is there a charge on this? No charge? Okay. So I can form another double bond, but if I do that, if I form a double bond, I'll have 2, 4, 6, 8, and then I'll have 10. Which means I'm going to have to get rid of a few of these electrons. Now I know this is probably a little bit confusing for you, but it has no charge, so I'm not getting an electron from an outside source, and I'm not losing an electron from within. Does that make sense? It's a neutral atom. Okay? Now this isn't going to make sense, but an atom will do whatever it needs to do to become stable. If that means these guys are going to transfer their electrons, they'll do it. See what I just did there? Okay, I know it's kind of like, well, I thought that things that bonded covalently didn't transfer their electrons. Well, that's the kind of a misconception. Okay, they're going to do whatever they need to do to become stable. They're going to arrange their electrons in however way possible to make them stable. And isn't sulfur going to be stable with 8 versus having 10? And won't the oxygens be stable if they have 8? You see how every one of these guys have 8? Now, we will talk about octet exceptions quite often in this particular chapter. Okay? But there are a few of them that have to obey the octet. Oxygens have to obey the octet. They cannot disobey the octet. Now, sulfur can disobey the octet, but if we were going to make sulfur disobey the octet, we wouldn't have had the oxygens wouldn't have been stable, would they? If I would have just formed a double bond and kept these 2 electrons here and didn't transfer them, are these oxygens stable? No. Okay? Sulfur does not have to have an octet, but in this case, it can be more stable if it gives its electrons, making the oxygen have an 8. Right? So, voila, voila. Okay? That helps a little bit. We'll do more of these when we get into the Lewis structures. I realize we haven't even talked about them, but I crammed them down your throat pretty hard in physical science and chemistry. I feel like that at least the normal ones you're all good with. We'll do some of the exceptions as we progress. Any last questions?